I'm going to be doing the Jumpstart drill. So I'm going to put a 1 minute timer here, and I'm going to try to solve this question, and we'll start the question and work on it for about a minute, and then basically that's going to be the Jumpstart. I'm not going to try to complete it. Just going to try to start the first minute of solving it. So we have a charge Q moves under the central inverse square force. F equals negative K over R squared, while also experiencing a weak uniform, I guess we'll go ahead and start the timer here, electrostatic field here. So E equals E naught Z. Derive the first order precession of the orbit per revolution caused by the field. Charge Q moves under a central inverse square force. So, precession of the orbit. I'm gonna guess that we kind of want the orbit equation for this, which would be something like, if I'm not mistaken, P divided by 1 minus epsilon, or this E thing, cosine of theta. And I don't really remember exactly what P is, but it might be like, it could be L squared over mu y. But in any case, we're looking for the first order precession. So I guess um, first order precession. Maybe we want something that's like R is going to be like equal to the R theta naught plus R prime theta naught theta minus theta naught plus R double prime at 1/2 here. And then doing some sort of a Taylor approximation, maybe. Not exactly sure how we want to start this. I don't really know what the first order precession is. I guess we've run out of time here, though. That wasn't really enough to do anything, so maybe I'll do 2 minutes. But let's just see, okay, how to solve. So I just want to jumpstart it and see if I got anywhere close to what I kind of want to do. It doesn't look like I was able to do anything like this. What is going on here? Uniform fields add. This might have been a little bit too difficult of a question, I guess. But they're saying something like taking the total potential, which is UR, equals negative K over R, which was given, and it's experiencing this field. So from the field, you get minus Q epsilon naught R cosine theta. And then from there, first unperturbed inverse square law. Perturbation equation. Unfortunately, I've never really heard of these things, so it might be a little bit too advanced to go into it. But that's okay. So this is a kind of adding these two potentials makes sense. Essentially would be the first step of this. So it's kind of difficult. Let's try this again with a longer timer. We'll add a minute, and we'll try the next question. All right, let's see if we can do this. So this is a rigid motor, rigid. Try to read the question first. So rigid rotor with moment of inertia I and a fixed dipole moment P is placed in a uniform electric field. We start from the Lagrange's equation. I don't know, dr. Maybe I'll just put Q for now. Um, assume that. Start the timer. Determine the exact stability condition and small oscillation frequency for alignment of the dipole with the field. Okay, so I know something about the stability condition is definitely like du over dr equals 0, perhaps? Now this could just be circular orbit, though. Hard to remember all these things. Exact stability condition and small oscillation frequency. Small oscillation frequency for alignment of the dipole with the field. Um, I remember that like you can find. Let me see if I got some notes on this or something like this, because we have the dipole moment can make a field force. Like over here, there's like a torque. Could say U negative P dotted with E. That's interesting. So negative P dotted with E. This gives us U, exact stability condition, the small x. So we can take a derivative here, maybe. And P, I know P is supposed to be Q, call it D or call it QR. So we can do that. Maybe we need an ER here. I'm not exactly sure. Oh, I guess it's a uniform field, so it's just going to be E naught. I don't have the eraser, so E naught. And let's take the first derivative, where U equals negative Q epsilon naught. So how does that help? Maybe that's the stability condition? What happened to our timer here? I guess the timer stopped. Okay, this is kind of an annoying timer because it doesn't really work very well. What are we supposed to do about that? I don't know. But anyway, since the timer stopped, let's see what the solution is. Let this be the angle between the dipole. Um, and we were close. We needed a cosine theta. Oh yeah, that's because the dot product requires the cosine theta. Okay. A Lagrangian. Let's just set up the Lagrangian. But we're trying to get the second derivative in terms of theta. So it would be the second derivative here rather than the first stability. I guess that makes sense. So second derivative to get that stability going, and then we needed this cosine for that. That's been able to get us in the direction that we're trying to go. I mean, we're not really trying to solve this. We're just trying to sort of figure out what the first sort of step is within our first 2 minutes. It'd be nice if we'd solve it all in 2 minutes, but I don't know, they're a little bit difficult. So let's try this timer again. And we can see it up here, but okay, new question. These are good difficulty questions, sort of learning some stuff. So a conducting sphere of radius r is placed in a uniform electric field E, using separation variables to determine the total induced dipole moment of the sphere. Induced dipole moment. Well, we have a guess at first because the induced dipole moment, like usually we have something like this as a dipole, but using the separation of variables means that we have to go like A. We know that this is going to be either R and then maybe B, this, and C with azimuth. But according to symmetries, we should be able to cancel out these things and be left with just V is equal to AR. That would make a lot of sense. So we're looking at something in the spherical velocity is 1 over r squared. And we have d over dr r squared a sub r. And then I think it's supposed to be equal to 0. Of course, we can multiply both sides by r, and then we can see that this should be constant. Call it v naught, I guess. Then we can divide this by r squared, and then we have to integrate this. so that we get something like negative V naught, sorry, negative 2 V naught over R to the third is equal to this V. I don't know, maybe this is, this is kind of what I came up with. Hopefully this makes some sort of sense. It's probably horrible, but that was 2 minutes. So how to solve this? The electric field didn't even do anything for us. Wow. I mean, I guess we're supposed to recognize why wouldn't this go away? It doesn't make too much sense. Let me just ask this. Why doesn't the theta be like theta go away? It's got angular symmetry, polar symmetry. What's the direction of this xenon? Of this E? No, it doesn't say. Direction of E. Mm, no, it's saying that it's E naught Z. I guess, oftentimes this E naught field is in the Z direction. If that were the case, then yeah, we don't get the polar symmetry anymore. That's something that I guess in a lot of problems, if they just say that it's a constant field E naught, I think it's just kind of a standard that we put this in the Z direction. So okay, I guess the idea for this problem was that we were supposed to recognize that we're supposed to consider that the Legendre polynomials here. So I guess this solution instead, AL r to the L plus BL r negative L plus 1. And I guess that kind of explains why we were off in the wrong start there. Okay, well, that was that question. Sort of figured out something out a little bit about this electric field. We're supposed to jump to this. Well, I would assume that this term, remember, this term should go away and we should be left with this term, which is exactly that. But anyways, go to the next question. Hopefully we get something that maybe we can slightly solve. Gonna set this timer again. We got 2 minutes and let's go. So particle of mass m moves in a central potential. So we have something like VR equals 1/2 kr squared minus alpha r. Using the effective potential, determine the radius and small oscillation frequency of the stable circular order. I think we know how to do this. Hopefully we can get this right because we have to take the effective potential here by adding L squared over 2m r squared. And then we want to take the stability condition. No, we want to determine the radius and small oscillation frequency. The radius of the stable circular order. I think here we take the dv over dr equals 0. I think this gets us a circular orbit. Hopefully it's not the second derivative again, but let's try this. So we get kr minus, this will actually be plus alpha over r squared minus L squared over mr to the third, and then set this equal to 0. So we just set that equal to that. Multiply everything by r to the third. How are we going to isolate this r here? Jeez. So kr to the fourth plus alpha r equals L squared. This looks rough. Um, yeah, I don't know how we'll be able to solve for r here. Well, that was the whole timer. So, okay. Yeah. So there we have everything set up there. We're computing the derivative, multiplying by r to the third. This vortex gives the stable orbit radius r naught. What? What? I forgot this over. Bro, how are we gonna solve this vortex equation? Bro, these questions, man. See, ChatGPT has really good questions that he asks. Like, man, how are we gonna solve this vortex here, dude? I don't know. Okay, but the oscillation frequency is the second derivative. Interesting. I didn't know that. I mean, I guess I kind of did. W squared m is really equal to the second derivative here. But it has to be at r equals r naught. So that's why I was kind of wondering how on earth I'd be able to solve it. But I guess they just shoved in r naught here and called it a day. Wm squared? Yeah, exactly. That's how it works. Because really you just have w equals the square root of u double prime divided by m. This is something to remember. Alright, so that was that. Let's try the next question then. This is a pretty cool exercise. I'm doing a little bit better, but not all that much better. Let's try a couple more maybe. Two identical masses m are connected by three identical shapes. No, what frequencies? Okay, so here, 2 minutes. Three identical strings with constant k. Well, this is an easy problem that we've done a million times, isn't it? We have identical masses, identical spring constants. Oh, this one's too easy. The normal mode frequencies. So what we have to do is set the Lagrangian. It might take a while. So m, let's call it m. We'll say x1 uh, is the velocity for x1. And x2 velocity. And then we have to set up the minuses for the spring potential, which are k x1 squared. I think we have to add a 1/2 k x1 squared, another minus 1/2 k x2 squared, and then we have the one that is x1 minus x2 squared, which gives us a little bit more complex terms here, but I guess I'll expand it. Be something like 1/2 k x1 squared minus 1/2 k x1 x2 minus 1/2. I think it's a plus 1/2 k x2 squared. Hmm. Well, it would be minus this, so then you actually get a minus sign here, and I think you get a plus sign here. so that this becomes kx1, and then this becomes kx2. We're out of time, but I wanted to actually do this a little bit here. So the idea is then we take the ddl over dx1 dot equals dl over dt dx, and we would repeat this, but I think there's a way to get this matrix. There was like a trick to getting the matrix really quick by getting rid of the 1/2s and focusing on the kinetic part. So I guess it would be mx1 squared plus mx2 squared. I think there might be a 0, 0 here because there's no cross terms. And then I think we just do this again here. Not 100% sure. It could be that it's more like this. And this might be the M matrix. But I could be completely wrong here. I'm just trying to hurry this up because we're out of time. K matrix, I believe, comes from this, which would be negative K. Here's a, yeah, so negative K on that one, negative K on this one from those. And then I think over here we have K and a K. This is just the cross term right here. All right, well, anyway, let's see if that's any close to what we need to do here. Just a little bit of practice. See if we got the matrix set up correctly. What's the M matrix and K matrix? Yeah, I was correct about the M. These are not part of the matrix, so they're actually supposed to come out. You have the M M and you have the 0 0, which is good. So all you did was we took just this stuff from the kinetic energies and we stick them into this matrix. And since there's no cross term, like there's no dots here, then these are just 0. Now for the K matrix here, I kind of messed it up a little bit. Did we mess up the Lagrangian? It's Lagrangian. K, negative K, negative K. Hmm, 2K, and then 2K, and then there's negative K, negative K. Well, we're pretty close. I'm getting a little bit confused about that. But as you can see, these are just a couple of quick jumpstart problems. I'm going to do a little bit more exploration on what happened here. So I guess we are basically out of space here, maybe. That was also kind of a long video, so we'll go ahead and wrap it up here for the jumpstart drills. And hopefully that was kind of interesting.